The next heading is the types of liquid solution. Liquid, 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 liquid solution. Liquid solutions are broadly two types: ideal solution, ideal solution, non-ideal solution, non-ideal solution. Non-ideal solution is further divided into a positive deviation from Raoult's law, or negative deviation from Raoult's law. Okay, now we will discuss the differences between these three types of solution. What is the ideal solution? What is the ideal solution? Ideal solutions are those solutions which obeys the Raoult's law over a range of concentration. We can write like this: obeys Raoult's law over entire range of concentration. This means the vapor pressure calculated from the Raoult's law is equal to the vapor pressure observed experimentally. The vapor pressure P of the solution observed, OBS observed or observed experimentally, is equal to the vapor pressure of the solution calculated 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 from the Raoult's law. This means the vapor pressure of the solution observed is equal to vapor pressure calculated from Raoult's law. We can write the like this: vapor pressure of the pure solvent A and the mole fraction of the that component A plus vapor pressure of the pure component B and the mole fraction of the pure component B. This is the vapor pressure of the solution calculated from Raoult's law is equal to the vapor pressure observed experimentally. Okay, here here the deviation, show the positive deviation from the Raoult's law, show positive deviation, or we can write do not obeys Raoult's law. Okay, do not obey the Raoult's law. Vapor pressure of the solution observed experimentally is greater than the vapor pressure of the solution calculated from the Raoult's law. Means the vapor pressure of the solution observed is greater than the vapor pressure of the solution calculated from Raoult's law. The vapor pressure calculated from Raoult's law for the solution can be write like this: vapor pressure of the pure component A and the mole fraction of that component A plus the vapor pressure of the pure component B and the mole fraction of that component B. The vapor pressure, this is the vapor pressure of the solution calculated from the Raoult's law. The vapor pressure of the solution observed experimentally is greater than the vapor pressure of the solution calculated from the Raoult's law. Okay, negative deviation, negative deviation do not obeys Raoult's law. This means the vapor pressure observed experimentally is lesser than the vapor pressure calculated from the Raoult's law. Vapor pressure of the solution calculated from Raoult's law. The vapor pressure observed experimentally is less than the vapor pressure of the solution calculated from Raoult's law. The vapor pressure calculated from the Raoult's law can be write like this: vapor pressure of the pure component A and its multiply its mole fraction A plus vapor pressure of the pure component B and its mole fraction and into the its mole fraction B. This is what the vapor pressure calculated from the Raoult's law. Okay, this is the basic difference between ideal solution and non-ideal solution, मतलब positive deviation and the negative deviation. The next point is based on the intermolecular force between the molecules of the molecule of the solute and the solvent. Second point is intermolecular force between molecules intermolecular force between the molecules. This intermolecular force is stronger. Vapor pressure vapor pressure is lower, means the vapor pressure is inversely proportional to the intermolecular force. In short, I write intermolecular force IMF. Intermolecular force is stronger, vapor pressure is lower. For example, a a a interaction, this A is the solvent, and BB means A is the solvent molecules, BB is the solute molecules. The this is the interaction, and BB interaction is equal to AB interaction, means this is solution, solute solvent. Well, this is solution. In the solution, solute and solvent interaction is in the solution. So here, in the ideal solution, solute solute molecule and solvent molecule interaction 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 is equal to solute solvent interaction in solution. This means the solute interaction or solvent solvent interaction is equal to solute solvent interaction in the solution. The solute molecules and solvent solvent molecule interaction is equal to solute solvent interaction in the solution. Okay, here 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 the vapor pressure observed is greater than the vapor pressure calculated from Raoult's law. This means the vapor pressure is we want high vapor pressure. This indicates that the intermolecular force between the solute and solvent molecule in solution is weaker. Because the intermolecular force is weaker, vapor pressure obtained is high. So this means that AA, मतलब solvent, and BB, the solute के molecules हैं BB, solvent molecules AA and solute molecules BB, interaction is stronger interaction है than the solvent and solute interaction in the solution, मतलब A and B solution से. This means the solute interaction and the solvent interaction, मतलब solute molecule and solvent molecules interaction is stronger than solute solvent interaction solute solvent interaction in solution. मतलब ये है कि जो सॉल्यूट और सॉल्यूट मॉलिक्यूल्स का जो इंटरेक्शन है, या सॉल्वेंट सॉल्वेंट मॉलिक्यूल्स का जो इंटरेक्शन है, वो स्ट्रॉन्गर इंटरेक्शन है देन द सॉल्यूट एंड सॉल्वेंट when combined and form the solution. Solute and solvent interaction in solution is weaker interaction है, तो interaction weaker होगा तो vapor pressure high हो जाएगा, तो vapor pressure increase. That is why we called the positive deviation from the Raoult's law. In negative deviation of Raoult's law, the solute ए मतलब सॉल्वेंट मॉलिक्यूल के बीच में जो इंटरेक्शन है एंड द सॉल्यूट मॉलिक्यूल के बीच में जो इंटरेक्शन है इज सॉल्वेंट सॉल्वेंट मॉलिक्यूल के बीच में जो इंटरेक्शन है और सॉल्यूट सॉल्यूट मॉलिक्यूल के बीच में जो इंटरेक्शन है वो वीकर इंटरेक्शन है देन द सॉल्यूट एंड सॉल्वेंट मॉलिक्यूल इंटरेक्शन इन सॉल्यूशन. तो दिस वी कैन राइट like this. the solvent solute solute molecule interaction, solute solute molecule interaction, solute solute molecule interaction, and solvent solvent molecules interaction is weaker than the solute solvent interaction in solution. Okay, that's why the vapor pressure of the solution decrease, and so the negative deviation. Okay, the next point is enthalpy change on mixing. Enthalpy change on mixing. What would be the change in enthalpy when we mix the solute and the solvent? For ideal solution, that the enthalpy change, there's neither heat absorbed nor a heat is released. This means the enthalpy change on mixing the solute and the solvent and form the solution is zero. So delta H mixing, मतलब change in enthalpy on mixing for ideal solution is always zero. This indicates that neither a heat absorbed nor a heat is released during the mixing of the solute and the solvent. In the positive deviation, the enthalpy change on mixing the solute in the solvent is positive, well, the heat is released. This is endothermic process. The delta H mixing is positive, means this delta H mixing is positive, means when we add a solute in the solvent, the heat is released. This means the heat is released. The process is called an exothermic process. Exothermic. No, 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 no. Delta H mixing positive means this process is endothermic. Heat is absorbed. Endothermic heat absorbed. Okay. And the for negative deviation, delta H mixing is negative. This means the process is exothermic. Process is exothermic, मतलब heat released when solute is added in the solvent and form the negative deviation from Raoult's law. In such a case, delta H mixing is negative. The process is endothermic. Heat is released. Okay. Next point. Next point is point fourth. एंथैल्पी ऑफ एंथैल्पी चेंज ऑन मिक्सिंग हो गया. अब नेक्स्ट पॉइंट, वॉल्यूम चेंज ऑन मिक्सिंग. वॉल्यूम चेंज ऑन मिक्सिंग, that is delta V mixing. Delta V volume change in mixing is equal to 0 for ideal solution. This is because when we add a solute in the solution in the when we add a solute in the solvent, there's no change in the volume. The change volume of the solute plus solvent is equal to the volume of the solution. There's no change in the volume because the interaction between the solute molecules and the solvent molecule is equal to solute solvent molecule. Okay. Volume change on mixing for a positive deviation, volume change volume change on mixing for a positive deviation, well, the delta B mixing for a positive deviation is positive. This means volume is positive. Volume increase. Why? Volume increase because when we add a solute in the solvent, the volume of the solution is greater than the total volume of the solute plus solvent. This is because after mixing the solute in the solvent, the molecular interaction between the solute and the solvent is weaker. When the solute and the solvent interaction is weaker, the molecules is far away. The molecules are far away. They occupied the more volume. That's why the volume change on mixing increasing in case of positive deviation. Okay, but in negative deviation, opposite of this negative deviation, delta B mixing is negative. Why? Let we look into the molecular level. When we add a solute in the solvent, the volume of the solution decreases because after addition of the solute in the solvent, the solute and solvent interaction in the solution is stronger. So when the solute and solvent interaction in the solution is stronger, means the molecules come closer, and thus they occupied a less volume and the volume become decreasing. That's why the delta B mixing decreasing for a negative deviation solution from the Raoult's law. Okay, now move on the next point. Now move on the next point and add a next page in this. Next point is next point is fifth point: change in the change free energy change. Yeah, gives energy change on mixing. The gives energy change delta G mixing for ideal solution is negative. Delta G mixing for positive deviation solution is also negative, or delta G mixing for a negative deviation solution is also negative. By all these three types of solution, so the negative gives energy change, because the negative gives free energy change means the process is spontaneous. Process when the mixing the process is spontaneous, the both the solution three all three solution are formed spontaneously. That's why the all three solution have negative delta G on mixing. Okay, sixth point, the next point: entropy change. Entropy change on mixing, well, means delta S mixing. Delta S mixing for all three solution is positive. Delta S mixing for all three solution is positive. Delta S mixing all three solution is positive. Delta S mixing positive means that entropy change is increasing when we add a solute in the solvent. This is true for all three solution, whether it is a positive deviation, whether it's so the negative deviation, whether it's so whether it is an ideal solution. All the types of solution, entropy change or randomness is increased when we add a solute in the solvent. Okay, our next point is the very important point, is the example the example of ideal solution, positive deviation and negative deviation. Example, we have to learn all these example because these example have been asked several times in your board exam. Examples for ideal solution, for example, benzene plus toluene. The name is similar, benzene and toluene, means those the example of the ideal solution belongs to the same family, means this benzene and toluene, or anhexane plus anhexane plus anhexane, या bromoethane plus iodoethane, bromoethane plus iodoethane. Last example is chlorobenzene or bromobenzene, chlorobenzene plus bromo benzene. Okay, you have to learn all these example are very important. Okay, in the positive deviation, ethanol mixed with the acetone, so the positive deviation, or ether in the water, ether plus water is the positive deviation. Okay, this is also the positive deviation, ethanol plus acetone, ether plus water, so the positive deviation. For a negative deviation, you have to learn phenol plus aniline, phenol plus aniline, chloroform plus acetone, chloroform plus acetone, or the last one is chloroform plus acetone of nitric acid plus water. This is all example taking from NCRT books, asked various time in your exam. Okay, this is all about the last and final point is the positive deviation solution is also so forms the minimum boiling point azeotrophs. This we can understand from the relation vapor pressure of the solution is inversely proportional to the boiling point. This is very important, have to remember this. Vapor pressure of the solution inversely proportional to the boiling point of the solution means here is the positive deviation. The vapor pressure is high means boiling point is low. The low boiling point means the minimum boiling point. So such a solution forms a minimum boiling point azeotrophs. We will discuss about the azeotrophs in after a few minutes later. Okay, here, the negative deviation solution forms the maximum boiling or exotop because the vapor pressure inversely proportional to the boiling point. The boiling vapor pressure here is low for a negative deviation, and boiling vapor pressure is low, boiling point is high. High means the maximum boiling point azeotrophs. So those examples we have right here for the positive deviation is also example for minimum boiling azeotrophs, and those example written here for a negative deviation is also example for maximum boiling azeotrophs. Okay, now have a look on the graphs. We plot a graphs between the vapor pressure of the solution, vapor pressure of solution versus mole fraction. Is a straight line graph, a straight line, or a linear graph for ideal solution. If we plot if we plot a vapor pressure of the solution Ps on the y-axis and the mole fraction on the x-axis, like this, mole fraction x-axis, suppose here only the components of B, only the components of A, here is only the mole fraction of the component A is 1, the mole fraction of the component A is 1, then the mole fraction of the component B is equal to 0. So at this point, only, only, only the component A is present, so only the component A forms the vapor, and this is called a pure vapor pressure, and the pure vapor pressure is represented by P naught A. Okay, here at this point, mole fraction of the component A is 0, then the mole fraction of the component B is equal to 1. So at this point only the mole fraction of the component A, and only the mole fraction of the component B is present. So only the moles of the B is present, the mole fraction of B only is there. That means the vapor pressure of the pure component B is represented by P naught B. Okay, as we go as we go left to right, the mole fraction of the component A decreases. mole fraction of the component A decreases. As we go right to left, the mole fraction of the component B decreases. Means the mole fraction of the component B is mole fraction of the component A is decreases from left to right. Then the partial pressure of the component A is also decreasing like this. From from this corner, the mole fraction of the component B is decreasing from right to left. Then the mole fraction of the component decreasing. The partial pressure of the component is also decreasing like this from Raoult's law. So this line indicates the partial pressure of the component B, and this line indicate the partial pressure of the component A, and the line joining the vapor pressure of the pure component A and B. This show the total pressure of the solution. This line indicates the total pressure of the solution. This is a complete graph for the ideal solution. Ideal solution graph gives a straight line. Similar graph when look for the positive deviation, they show a non-linear lines like this. Similar xa is equal to 1, xb here is 0, xa is equal to 0, xb is equal to 1. So if we first we draw a graph for the ideal solution p naught a, p naught b. then we draw a then we draw a graph for a positive deviation. In positive deviation, all these line bands up like this, bands up like this, bands up like this. Okay. Positive deviation graphs looks like this, and the negative deviation graphs look like this. First we draw a graph for the ideal solution like this, like this, like this. This is the graph for ideal solution. So if we draw a line like this, then the graph will come for negative deviation like this, like this. These graphs are for the negative deviation. Okay. So we have discussed the graphs of the positive deviation, negative deviation, and and the relation between these graphs. Now we moves on the azeotrophs mixture. Now we moves on the azeotroph mixture. What is azeotroph mixture? Azeotroph, azeotrophs, sorry, oh sorry, azeotrophs solution. Azeotrough solution is also called constant boiling point solution or constant composition solution. What does it mean? This means this means azeotrough solution are those solution which have a no change in the boiling point of the solute or the solvent after mixing. Suppose a solute has the boiling point, solute and the solvent have a same boiling point after mixing and form the solution, and the composition of the solution in the composition of the solute and the solvent in the liquid phase is same as the composition of the solute or a solvent in the vapor phase. Okay. Solution or mixture boils. Now we can define the azeotrope solution. Azeotropes, azeotrope solution, the solution, the solution or a mixture boils at a constant temperature and have constant composition in liquid and vapor phase. Vapor phases is called azeotrope solution. Types of azeotrope solution. Types of azeotropes solution. Azeotrope solution are two types. Number one is minimum boiling point azeotropes. The solution, the solution shows positive deviation from Raoult's law forms minimum boiling point azeotropes. For example, ethanol plus water, and ethanol must be 95% by mass. Ethanol plus water forms the minimum boiling azeotropes. The solution azeotropes, the solution which have a constant boiling point as well as the constant composition in the solution as well as in vapor phase. Okay. Second is the maximum boiling azeotropes. Maximum boiling azeotropes. The solution shows negative deviation from Raoult's law forms maximum boiling azeotropes. Very important example for the negative boiling azeotropes is nitric acid in water. Nitric acid 68% by what by mass and 30%, 32% by mass is water. This solution boils at the temperature. Boiling point of this solution is 393.5 K. Okay, this is the maximum boiling at azeotropes. One of the most important point for the azeotropes properties, azeotropes solution cannot be separated via the fractional distillation method because both have a both the component of the solution have a same boiling point, the constant boiling point. Therefore, such a type of the solution cannot be separated from the fractional distillation method. To add one point more in this, such solution, well, azeotrope solution cannot be separated into its component by fractional distillation method. Okay, we can add this in this. Now we have completed our vapor pressure concept. We have completed ideal solution, non-ideal solution, positive deviation, negative deviation, and azeotropes.